this. There we go. I always forget to record. Okay, so we're going to analyze this graph and this function by using limits. So whenever we approach limits, there's always a left-hand limit and there's always a right-hand limit. So that's why you see the two XY charts here. So the first XY chart is going to be for the left-hand limit. And what it means to be a left-hand limit means that we approach the numbers from the left side of the x-axis. So what we want to do here is find out what the limit is as x approaches 1 from the left. So we're going to analyze this function at 1. And the reason we're analyzing this function at 1 is because we have a point that is not defined, because our domain says we can't be equal to 1. So we're going to analyze this limit from the left. And what that means again is when you approach a number from the left, you are coming from the left side of the x-axis. So we are going to come from the left side of the x-axis and get really, really close to 1. But because of our domain, we can't land on 1. So what we're going to do is pick numbers to the left of 1 and put them in our XY chart. And we don't have to get too crazy. We don't have to fill the whole boxes out. So I'm going to pick a number to the left of 1, and I'm going to start with, how about -1. And then I'm going to get closer and closer to 1. So after -1, I'm going to pick 0. And then after 0, I'm going to choose decimal numbers that get me really, really close to 1. So I'm going to say, all right, let's choose 0.5. Let's choose 0.7. Let's choose 0.9. And now how about we choose 0.99? And then how about 0.999? And then I'm going to choose 1, even though the domain is telling me that I can't. And there's a reason for this. So all I want you to do now is take all of these numbers and plug them into this function x plus 1. So basically, all we're going to do to all these numbers is add 1. So -1 plus 1, that's 0. 0 plus 1 is 1. 1.5, 1.7, 1.9, 1.99, and 1.999. Okay, and then of course, if we plug in 1, we are going to get a y value of 2. Okay, now to understand what we just did, well, let's go ahead and look at the XY chart, and we're going to look at the graph as well. So looking at my XY chart, we see that for my x values, as x gets closer and closer to 1, we see that y is getting closer and closer and closer to what number?
2.
2. Good. So I'll run that back one more time. As x gets closer and closer to 1 from the left side of the graph, we see that y gets closer and closer and closer to 2. But we have to ask ourselves, can we actually use the value of 1? And that answer is no, because we were given a restriction that x cannot equal what value?
1.
1. Therefore, this point would be considered undefined. And we'll get to all this reasoning in a second. I just want you to know how to use a limit and know how to read a limit. So we see from our XY chart, once again, that as x gets really close to 1, y is getting really, really close to 2. Now let's look at our graph. I'm going to go over that. So we had a numerical representation, and now we're going to have a visual representation. So now, once again, I'm going to say it just like the numbers. As x gets closer and closer to 1 from the left, again, we see y getting closer and closer to what number?
2.
2. There you go. So what we have just found is called the left-hand limit. And the way to write the notation for a left-hand limit, I'll go here and I'll go, how about this? So for our left-hand limit, oh, come on, computer, catch up. We're going to say the limit as x approaches 2, as x approaches 1 from the left, and you see that little minus sign above the 1. So as x approaches 1 from the left, so the minus sign represents we're approaching numbers from the left, of the function x plus 1 will equal 2. So this is our limit notation for a limit that approaches from the left side. Now, we have to explore this function using a right-hand limit. So I'm going to go ahead and erase these. And now, if we are using a right-hand limit, this means that we approach the number from the right side of the x-axis, meaning all the numbers are bigger than the number we are approaching. And again, we are analyzing this function at 1. Okay, so we are approaching from the right side. Therefore, this second part of your XY chart represents the right-hand limit. And what I want to do is choose numbers to the right of 1. So why not? I can start off with 3, and then I'll go to 2, and then I'm going to choose numbers really close to 1. So I'll say, how about 1.5, 1.3, 1.1, and then let's get really close to 1. Let's say 1.01, 1.001, and let's just choose 1. Okay, and now again, plug this into the function x plus 1. So all we're going to do is add 1 to all these numbers. So we'll have 4, 3, 2.5, 2.3, 2.1, 2.01, 2.001, and of course, 2. So just like the left-hand limit, I'll read it again. The right-hand limit, as x gets closer and closer to 1 from the right side, once again, we see y is getting closer and closer and closer to what number again?
2.
2. Good. That is our right-hand limit. But once again, by our domain restriction, we can't use this number because, again, that point is still undefined. And then let's go ahead and look at the graph again. So we just saw a numerical representation, and now let's look at a graphical representation. So we see, again, for my limit, as x approaches 1 from the right side, we see that y is getting closer and closer and closer, again, to that value of 2. So our right-hand limit is also 2. And the way we notate that is we say the limit as x approaches 1 from the right side. So that plus sign means we are approaching 1 from the right. We are approaching a number from the right side. And the limit as x approaches 1 from the right of x plus 1 will equal 2. Okay. So we now have a left-hand limit at 2. We now have a right-hand limit at 2. And now this brings us into a very important theory that if a limit from the left and a limit from the right are equal, then this means that a limit from both sides must also be the same number. So basically, if the left-hand limit is 2 and the right-hand limit is 2 at x equals 1, this means that the limit at x as x approaches 1 from both sides will also be 2. So the way we write that is we will say, since these are equal, we will say the limit as x approaches 1 from both sides. So now we see there's no plus or minus. If there's no plus or minus, this means that this limit is from both sides. So we say the limit as x approaches 1 from both sides of x plus 1 will have to also equal 2. And this is how a limit from both sides exists. It only exists if the left-hand limit and the right-hand limit are equivalent. And therefore, if they are, we can say the limit from both sides is also 2. Okay. So this is how limits work. Basically, to break it down really, really simple, to just put it in plain English, all we're going to say is that as x approaches a number from both sides, all we want to know is what is y up to? What is the behavior of y? So for this problem, we can say as x approached 1 from both sides, y was getting closer to 2. And that is how a limit works. As x approaches something, we want to know what number y is approaching. And that's all that matters. So that's how we work a limit. Okay. Go ahead.
So is the limit just to find out what y is doing? That's the whole purpose of it?
That's the whole purpose of it. And I guess another thing, if you want to go a little deeper in here, so we see how the point is an open circle, meaning the point is undefined, right? So how can a point be undefined, but how can a limit exist? So that's something that we'll learn in the next lesson. So we can have a limit anywhere, even if a point is defined or undefined. Okay. And down below is just more information on the informal definition of a limit, just how it's written and how it's stated and what it means. But we already went over all of that. So the notation down here, all this says is the limit as x approaches some number c from both sides, the function f of x will equal some number L. So again, what we worry about with the limit is as x approaches the number, what is y doing? What number is y getting close to? So that's what these two say here. As y approaches the limit, or y approaches some number L as x approaches some number c. That's it. Nothing crazy. All right. Any questions on this page before moving on? All right. So next page is a little bit of more definition, but it's just going over everything we just learned on this last page. So our first definition is the left-hand limit. And I explained to you everything about a left-hand limit. So the first thing is the notation. The limit as x approaches c from the left, you see that little minus sign there? That means you're coming from the left side of the x-axis. The limit as x approaches c from the left of f of x will equal some number k. So if you approach c from the left, this means that as x approaches c, all the values of x are smaller than that number you're approaching. So let's go look at it. I'll go back to the first page. So what's that saying is that as we approached 1 from the left on our last example, all of these numbers to the left of 1, these are all smaller than 1. So that's what it means to be a left-hand limit and how to read a left-hand limit. All values of x are smaller than the number we're approaching. And the same will go for the right-hand limit, which is the next definition on that page. So it says the limit as x approaches c from the right, and remember that plus sign is there to show you it's coming from the right. Well, if you approach something from the right, just know that all the numbers to the right of the number you're approaching are bigger than that number you are approaching. And that's how a left-hand limit and a right-hand limit work, but we already know how they work because we used them on this example. We use the left-hand limit and we use the right-hand limit. Okay. And then if no direction is specified in a limit statement, then we assume that the limit is two-sided or unrestricted. So basically, if you don't see that plus or minus sign, then this is telling you to take a limit from both sides. And then next is called the Theorem 1, the existence of a limit. We went over that too on that past example. Basically, what this says is for a two-sided limit to exist, the left-hand limit and the right-hand limit must exist and must be equal. That's what we did on that last page. So this says the limit as x approaches c of f of x will equal some number L if and only if the limit as x approaches c from the left and the limit as x approaches c from the right equal the same number L. And that, again, is what we did on the first page. Right there. Come on, laptop, keep up with me. There it is. The left-hand limit was 2. The right-hand limit was 2. Therefore, the limit from both sides is also 2. Okay, so those are definitions going everything we just covered already. The definition of a left-hand limit, the definition of a right-hand limit, and the existence of a limit from both sides. Okay. Now on this next example, all this wants us to do is learn how to apply limits to a graph. So it's asking us to apply the limit and give it an output. Give the limit as we approach some value of x. So we're going to start with A. And A says, what is the limit as x approaches 2 from the left? So what we have to do is reference the graph on the right. And let's go ahead and find the number we are approaching. We are approaching this 2 from the left side. So what's it saying is as we approach 2 from the left, what value is y getting closer and closer to? And what value is that?
Two.
2. Good. Again, it's kind of like you're tracing. You're tracing your x and y's at the same time. So again, as x gets closer to 2, y is getting closer and closer to 2. So for the first answer, we get the limit from the left at 2 is going to be the y value of 2. Okay. And then let's do it again. Let's go ahead and answer B. This says, what is the limit as x approaches 2 from the right? So here, we're going to approach 2 from the right. And as we approach 2 from the right, well, what value is y getting closer to now?
5.
Good. 5. We're getting closer and closer to 5. So my answer for this one is 5. Okay. And then C, we don't even have to look at the graph anymore. We can just apply the existence of a limit theorem right above on our paper. So C says, what is the limit as x approaches 2 from both sides? And this, we have to use the existence of a limit theorem on it. So if we're looking at our two answers above, what is the limit from the left as x approaches 2 from the left?
2.
2. And what is the limit from the right?
It would be
5.
equal.
5, right? The limit is 5. So in order for our limit to exist from both sides, the left-hand limit has to be equal to the right-hand limit. Are these equal to each other?
No.
No. Therefore, the limit from both sides can't exist. So for C, we would say the limit from both sides does not exist. And this is only because the left-hand limit is 2, the right-hand limit is 5, and therefore those are not equivalent. Therefore, the limit from both sides can't exist. Okay. Any questions on those so far? So that is just learning how to apply a limit, how to read a limit and read a graph together. Okay. And now the very last question has nothing at all to do with calculus. All this question says is, when x is exactly 2, what is the value of y? So all it wants is a y value, no limits involved. When x is 2, what is the value of y?
2 and 5.
Good. But in this case, it's just going to be 2. And the reason for that is because this is a closed circle and this is a open circle, which means if it's an open circle, that point is undefined, meaning we can't state 5 as an answer. Does that make sense?
Yep.
Yep.
Excellent. Okay, awesome. So most of your homework problems will probably look like this. You'll be reading a graph and trying to find the limit. Well, probably a couple of them, but any questions on this problem before moving on? All right. Okay. The next page is just about all the algebraic properties you can apply to limits. All the algebraic properties you can apply to limits. So just remember that calculus is heavily algebra based. So why wouldn't we be able to actually apply algebra to limits? So I'm just going to run through these properties real fast. Property number 1 says the limit as x approaches c of some constant k, that limit will equal the constant. So basically the limit of any constant is the constant. And remember, a constant is a number. It's just a number. It's a number without a variable. So to represent number 1, I'll just do a little example here. If I said the limit as x approach some number c of 5, 5 is a constant, what would the limit of 5 be?
5.
That's it, 5. That's all. That's all it says. So if you have the limit of just a number, then the limit is that number. So the limit as x approaches c of 5 is 5. It could be the limit of 100 and the answer would still be 100. That's all that's saying. Okay. 2. This is called the direct substitution property for limits. This says as the limit as x approaches c of x equals c. So all this property says is, hey, take whatever value x is approaching and plug it in for x. So to represent number 2, if I said the limit as x approaches, let's say 2 of x, all this limit says is, hey, take this 2 and plug it in for that x. So what would my limit be here?
2.
That's it, 2. And we go for any number. If it was as x approaches 5, x approaches 10, x approaches 15, it would just be that number. Okay. 3. All this says is the limit can be applied over multiple terms held together by addition or subtraction. So this says the limit as x approaches c of f of x plus or minus g of x can be split into multiple limits, meaning it becomes the limit of f of x plus or minus the limit of g of x. So you can apply the limit to multiple terms. That's all this property is saying. So to represent number 3, if I said the limit as x approach 0 of x squared plus x, all I have to do is rewrite it as the limit as x approaches 0 of x squared plus the limit as x approaches 0 of x. That's it. That's how you would use it. So you can apply the limit over multiple terms. So if there was 3 terms in there, I would have 3 limits. If there's 4 terms in there, I would have 4 limits, and so on and so on. And it doesn't matter if they're connected by addition or subtraction. Okay. So that's just saying you can split your limits up. 4. This says the limit as x approaches c of k times f of x, some constant times a function, can be rewritten as k times the limit of that function. So all this property says is, hey, you can rearrange your limit by moving the number in front, by moving the number attached to your function in front of the limit. So a good example of that, let's just say I did the limit as x approaches c of 5x squared. All this property says is, hey, take this 5 and move it to the front. So I can rewrite this as 5 times the limit as x approaches c of x squared. That's it. I just take that number and move it to the front. Okay. And number 5 is just like number 3. I can apply the limit to multiple terms, but this time connected by multiplication. So for this one, it says the limit as x approaches c of f of x times g of x can be rewritten as the limit of f of x times the limit of g of x. So a good example of that, let's say I had the limit as x approached c of x plus 1 times x minus 1. So I'm just going to just do 2 terms, keep it simple. I can rewrite this as the limit as x approaches c of x plus 1 times the limit as x approaches c of x minus 1, and so on and so forth if I had more terms. Okay. 6. Well, 6 is like 3 and 6 is like 5. So 6 says I can now apply the limit to a fraction. I can apply the limit to a numerator and a denominator separately. So this says the limit as x approaches c of f of x over g of x will equal the limit of f of x over the limit of g of x. So this just puts the limit to the numerator and denominator. So again, let's say I did the limit as x approaches c of x squared over x plus 1. There's my fraction. All I have to do is rewrite it as the limit as x approaches c of x squared over the limit as x approaches c of x plus 1. That's it. You can apply that limit to the numerator and to the denominator. And the very last property, number 7, says I can apply the limit inside a radical of any power. So we say the limit as x approaches c of the nth root of f of x is equal to the nth root of the limit of f of x. So all we did was take that limit and put it inside the radical. So to represent number 7, if I said the limit as x approaches c of the, let's say, 4th root of x plus 1, I can rewrite this as the 4th root of the limit as x approaches c of x plus 1. That's it. You just take the limit and apply it inside the radical. Okay, those are your limit properties. They let you know everything you can do to a limit, which is great because they're all algebraic approaches. Okay, so now we know all these properties. We're going to definitely apply them below, but I think we have two more properties, which aren't crazy. So the next theorem says the limits of polynomial and rational functions. Number one says the limit as x approaches c of f of x will equal f of c for any polynomial function. So this is just like the direct substitution property I said above. If you are dealing with a polynomial, all this says is take this value of c and plug it in for x and move on. Oh, simplify and move on. That's it. That's all that says. So it is just another direct substitution property. The same with number two. The limit as x approaches c of r of x will equal r of c. Once again, take this value of c and plug it in for x. But this one has just a slight restriction on it. It says for any rational function with a non-zero denominator at x equals c. That means if we were given a fraction, which is a rational function, whatever number we plug in for x, whatever number we plug in for x can't make the denominator 0. That's all this says. So if it makes your denominator 0, we have to go back and see how we can fix the problem. So that's all this says. So whenever you plug numbers in, if you ever get a 0 in your denominator, this means we have to go back and try to fix it algebraically. Okay. So those are all the properties of limits. So let's go ahead and apply them below. Don't worry, it's not scary. Yet, right? Okay. Number one, find the limit as x approaches 3 of x squared minus 4x. Well, this is a polynomial function. So if we use the property we learned above just right now, all that property says is, hey, take 3 and plug it in for x. That's all we have to do. So I'm just going to rewrite it. Let me move down here. You're going to have the limit as x approaches 3 of x squared minus 4x. And all this direct substitution property says is, hey, take that 3 and plug it in for every x. And simplify. That's it. You'll get 9 minus 12, and we get our limit value of -3. Any questions on that?
No.
Calculus is seeming way too easy now, right? All right. Let's do it again then. Number 2. Find the limit as x approaches 1 of 5x plus 4. Well, once again, we can go ahead and make this fast. And what number will you plug in for x?
1.
That's it.
This is the same property as number 1.
This is, yeah, I mean, you can, it's not a polynomial, but it'll follow the same property of, hey, just plug that number in. So, whoops. So this will just become 5 times 1 plus 4, which will give me the square root of 9, which will give me 3. So I guess to sum all these properties up, all you have to do is plug in that limit value and hope it works. Okay. There's 1 and 2. So once again, you just plug in the number and simplify. All right. Now we get to 3. Let's go ahead and do it again. So this says the limit as x approaches 4 of x minus 2 over x. Well, guess what? What number will you plug in for x? 4. That's good. of x minus 2 over x, I'll get 4 minus 2 over 4. I'll get 2 over 4, and my limit is 1/2. There you go. Couldn't be any easier, right? All right. Now let's do it again. All right. 4. Find the limit as x approaches 2 of x squared minus 4 over x minus 2. So once again, what number will you plug in for x?
2.
2. Life is great, right? We're just plugging numbers in. So plug in 2, but what happens when I plug in 2 to this problem?
0 in the denominator.
You get 0 in the denominator, and you get 0 in the numerator. So does anybody know what 0 over 0 is called?
No.
And it's okay if you don't, because 0 over 0 is definitely not 0. 0 over 0 is a special type of form. This form is called indeterminate. This is an indeterminate calculus form, which means if you ever come across an indeterminate answer, we have to go back to the very first step and figure out if we can fix it algebraically. So let's rewind. I'm going to rewrite it again. And this time, let's see if we can fix it algebraically. Does anybody notice anything special about this numerator?
Can't you just simplify the x stand by 2? Just get x minus 2 instead of
Where?
a fraction.
We're at? Or like just end up completely with x minus 2?
Yeah.
So how would we get there?
Because can't you remove the x on the denominator because of the squared? So it's just x.
So like do something crazy like that. Oh wait,
Yeah.
it's not showing. Hang on. Come on, laptop. Uh-oh. I think we're frozen. There we go. Do something crazy like that.
Yeah.
Unfortunately, we cannot because the terms are connected by subtraction. So we could do it if it was just x squared over x. We could do it. But since it's x squared minus 4 over x minus 2, we can't cancel like that. So we have to think of one other way to go about it. And like I said, x squared minus 4 is something special. It is a difference of
Squares.
squares. And what could you do to a difference of squares? What's that
Factor.
special F word? You said it.
Factor.
Factor. FOIL's the other way. Factor. What is x squared minus 4 factored to? Oh, I gave it away. What two special numbers make 4 when you square them? Or what one special number makes 4? It's 2 and 2, right? So a
Yeah.
difference of squares will always factor to x plus 2, x minus 2. And now, since we have factored it, what else do you notice? What could we do here?
You can cancel out the x minus 2.
Very good. And this will leave us with the limit as x approaches 2 of x plus 2. And now all we have to do is plug in 2. And if I plug in 2, what is my final answer?
4.
4. Now, 4 looks very different from 0 over 0, right? So there's our answer. So if you ever come across an indeterminate form, then you have to go back to step 1 and see how you can algebraically fix it. And for you guys, since this is business calculus, I think the most you guys will come across is factoring problems. You'll have to factor them and then reduce and then plug the number in. Okay. Any other questions on this one? All right.
If it was something you couldn't factor, how would that work?
Then it would probably just, so if you couldn't factor and you got like 1 over 0, then that limit would be, you would say does not exist. So if you try to exhaust everything you could and nothing worked, then the limit would not exist.
Okay.
Good. No, good question.
I got one question.
Yeah, for sure.
So on the canceling thing, what if you were to think about it as like, since you're dividing, you switch the sign to make it positive? It's like when you divide by negative, you switch the sign.
Like, what do you mean?
To get the x plus 2.
So you want to turn the denominator into x plus 2? Is that what you're saying?
No, never mind. It's fine. Never mind.
Okay.
I don't want to complicate anyone.
Okay.
Never mind. Sorry.
You're good. Okay. Now let's get to our last one and practice what we preach. The limit as x approaches 3 of x squared minus x minus 6 over x plus 2. Let's go ahead and just plug in that 3 and see if it works out for us. And if it doesn't, we'll have to factor it. Okay, 9 minus 3 minus 6 over 5. And 9 minus 3 minus 6 gives me what?
0.
0. You get 0 over 5. Hey, and what is 0 over 5?
I'm guessing an indeterminate.
You're thinking too hard. Just think a little.
0.
What is 0? 0 over any number is?
0.
0. Don't be tricked, right? So 0 over any number is 0, and 0 is a fine limit to have. So to make note of things you may come across, remember that 0 over any number is always 0. But then any number over 0 is considered undefined. Or since we have to talk in calculus terms and limit terms, it's going to have to be considered that the limit does not exist. And then the last form that you may see is, of course, 0 over 0, which we just found out is called indeterminate. And majority of the time, you can fix indeterminate. I'll say 99% of the time. And then if you ever get undefined or does not exist, then there's probably no possible way to fix it. Okay, so those are forms you may come across. Well, we already came across the 0 over 0. Okay, so any questions on that page? All right. Okay, we come to our last page. All right, so this activity is connecting limits to piecewise functions. And if you forgot what a piecewise function, well, the function they give us is a piecewise function. And piecewise functions are made of multiple functions with multiple restrictions. So this right here is a piecewise functions. It has two functions in it and two restrictions that go along with the function. So in order to use the first function, any x value we choose has to be less than or equal to 2. In order to use the second function, any x value we choose has to be greater than 2. So now here is an activity, once again, on how to connect limits to piecewise functions. So you have to understand the definition of what a left-hand limit and what a right-hand limit is. So if we look at the first question, this says, find the limit as x approaches 2 from the left of f of x. So if you understand a left-hand limit, so if x approaches 2 from the left, and remember, whenever you approach a number from the left, are the numbers smaller than 2 or will the numbers be greater than 2?
Smaller than 2?
Smaller than 2. Great, which means that this limit will connect to this restriction, because this restriction says that all your x values are smaller than 2, right? And if this limit connects to that restriction, this means we get to use which function? We get to use x squared plus 1. So we make all those connections. Since this limit matches up with that restriction, this means for the limit, we get to use that function x squared plus 1. So I'm going to rewrite this as the limit as x approaches 2 from the left of the function x squared plus 1. And all we have to do now is plug in what number for x?
2.
That's it. And you'll get 2 squared plus 1. So the limit from the left is 5. Good. Okay. Now let's do it again. The next one says, what is the limit as x approaches 2 from the right? If you approach 2 from the right, are your x values going to be less than or greater than 2?
Greater.
Good. Greater. Because remember, a limit from the right, the numbers are greater than that number you are approaching. So this limit matches up to this restriction, meaning which function do we get to use?
X minus 1.
X minus 1. Good. And I'll rewrite this limit down below. And we're going to have the limit as x approaches 2 from the right of my new function x minus 1. And once again, all we have to do is plug in what number for x?
2.
And we get the limit from the right is 1. Okay. So that is practice in matching limits to restrictions on a piecewise function. And it's all about understanding a left-hand limit and a right-hand limit. And now number 3, we're not even gonna look at the piecewise function for number 3. Number 3 is gonna use the existence of a limit theory. And number 3 says, find the limit as x approaches 2 from both sides. And for this limit to exist from both sides, the left-hand limit must be equal to the right-hand limit. So for this question, what is my left-hand limit?
Would it be
5.
5?
Good, 5. What is my right-hand limit?
1?
1. Are those equal?
No.
No. So this means that the limit as x approaches 2 from both sides of f of x, in the words of the great Lindsay Lohan, the limit does not exist. Mean Girls, anybody? No? No?
I get that reference.
There you go. And again, the limit doesn't exist from both sides because the left-hand limit's 5, the right-hand limit is 1. Okay. And then the very last question, again, has nothing at all to do with calculus. This is a purely algebraic question. And the very last question says, hey, when x is exactly 2, what is the value of y? So we have to look at our piecewise restrictions and which restriction allows us to be exactly equal to 2, the first or the second one?
The first one?
The first one, because what does that inequality say?
Less than or equal to?
Less than or equal to. So does that allow us to be equal to 2?
Yes, sir.
Excellent. So this means that since x can be exactly equal to 2, all we have to do is take 2, plug it into x squared plus 1, and what is my y value?
Five.
That's it. Nothing else. So that is how you connect limit restrictions to piecewise functions. And that is it for today. So if you have any questions over these notes, let me know. If you have any questions over the homework, let me know. We have what, 20, now like 14 minutes left. No, 20 minutes left, something like that. Other than that, if you are good to go, then we are done for the day, and I will see you guys on Monday. What does that say? Am I old for getting that reference? Just cultured. Cultured for watching Mean Girls, that's right. Okay. But if you have questions on this, stick around. If not, we are done, guys.
So I have a quick question.
Yes.
Just so I know how to do my homework if